All right, here we go with number 7 on our projectile motion review. Number 7 tells us that an object is punted at 25 meters per second, 40 degrees north of east, that's going to be important, on G's home planet. We want to know the range of the object on level ground, and it tells us what the acceleration due to gravity is. So this is another example of a time where we cannot use 9.8 meters per second squared as our vertical acceleration because we're not on Earth. We're on G's home planet, and that value is 18. So let's set up what we know and what we need. So let's make our XY grid here. A is still going to be 0 in the X direction. That has not changed. But A here is 18 meters per second squared instead of 9.8. It is, however, still negative because locally gravity pulls things down. And as we're used to, we're going to say that down is negative. So we still have that piece. Now we're also told that the projectile is punted at 25 meters per second. That is my hypotenuse value, 25 meters per second, at 40 degrees north of east. Well, north is up here, east is here, right? So north of east means I'm going this way, 40 degrees. And I need to figure out my initial y component and my initial, and thus final, and constant x component. So the first thing I'm going to do is figure out what the y component is by doing my hypotenuse of 25 times the sine of 40 degrees. And my x component will be 25 times the cosine of 40 degrees. Again, if you're confused as to why we're using sine or cosine, in particular for each one, or why we set it up the way we have with the hypotenuse, then make sure to get some help in tutoring there. So using my calculator, again in degree mode, I know that my initial y velocity is 16.07 meters per second, of course, and my x velocity is 19.15 meters per second. You may have rounded slightly differently than I did. All right, so let's keep going here. Let's put those values in my table. 19.15 and the IY is 16.07. And let's see if there's anything else that I know. I want the range of the object on level ground. So again, if the object is launched and completes its full path, comes back to level ground, then my delta y is 0. Because it ends at the same height from which it started. Okay? So knowing that delta y equals 0, let's use my kind of go-to delta y equation of delta y equals VIY t plus 1/2 AT squared. Delta y is 0, we plug that in. VI, I'm using y, so I have to use the y value I have here, which is 16.07 times t plus 1/2 times negative 18, not negative 9.8, t squared. Again, you get to this point where you can graph it, you can solve the quadratic equation, however you wish to do that. If you're confused about this step, just like in number 6, I'll ask that you either see your math teacher or Ms. McCaskey or myself for help on how to solve a quadratic equation. When I graph it, which is my method of choice, I get that t equals 1.79 seconds is my only physically viable option. The other one does not make physical sense. And then to figure out the range, I'm going to plug that into delta x equals vi, or rather vf, or vx, because again it doesn't change, times time. My x velocity was 19.15 times my time of 1.79 seconds gives me a delta x of 34.28 meters. That is the range that this projectile flew on G's home planet.